Hey everyone, I am Miss Hu, your physics teacher. In this video, we're going to go through nuclear emissions and radioactive decay. What we'll be covering in this video lesson are basically what the three radioactive emissions are, as well as their characteristics and properties, and also the concept of radioactive decay and the related equations. This is a topic in both the SPM and IGCSE physics syllabus. There's of course a lot more to know, so if you'd like to find out more, please feel free to do your own research or watch my other educational videos. What this video will be covering is just the overview of the information you will need in order to answer the questions in your examinations. So let's get started. Let's make my face a little bit smaller here first. Now, before we go into the nuclear emissions concept, we must first of all know what radioactivity is or where it comes from. Okay, radioactivity is actually due to unstable nucleus. If you recall what you have learned about isotopes, you should know that there are basically stable isotopes as well as radioisotopes. Now, radioisotopes are radioactive isotopes. If you can't remember what isotopes are, or if you have not learned it, please watch my video on the nuclear model and isotopes. For this video, we're just going to get right into the concept of radioactivity. So generally, we know that radioisotopes are radioactive. So we're going to focus here on radioisotopes. Now, what makes radioisotopes different from the other non-radioisotopes? So radioisotopes are radioactive. And the reason why they're radioactive is because they are unstable. So those that are not radioisotopes are stable isotopes. What do we mean by stable and unstable in this case? Okay, just a quick recall. I'm going to be using my iPad to draw here, so there may be a slight delay in what appears on screen and what I am saying. So let's say, for example, let me use the circle option here. Let's say this is the nucleus. So remember, for radioactivity, we're focusing on the nucleus. We're not looking at the electrons in the shells and all that. No, we're just focusing on the nucleus. And inside the nucleus, as you should know by now, there are protons and neutrons. Let's say these are all the protons inside this nucleus. And what I'm drawing now are the neutrons. Okay, so what you need to understand is that when it comes to radioactivity, we will only be focusing on what's inside the nucleus. We don't care what's outside. So all the electrons that are in the shells outside, we don't bother about that. We're going to focus only on what's inside the nucleus, and inside the nucleus are only the protons and neutrons. So why a nucleus is unstable is because of the number of protons and neutrons. You don't really need to memorize the numbers, but what you need to know in general is that in nature, there is a certain number of protons and neutrons that need to exist in certain elements for them to be considered stable. If you learn chemistry, you can refer to this number in the periodic table. So for example, carbon should have 6 protons, 6 neutrons to be stable. If the number of protons and neutrons do not match this number, then it's unstable. For example, if you have 6 protons, 8 neutrons, then it's not stable anymore. So different elements have different numbers. You don't need to know the number, just be aware every single element has a particular pair of numbers in terms of the protons and neutrons that it needs to have in order to be considered stable. If that particular nucleus does not have that number, then it's unstable. In most cases, many of the nuclei are unstable because there are too many neutrons. So it's too heavy. There's like too many things inside. And the number of neutrons here is like not exactly the correct number, so that it becomes unstable. So when something is unstable, it's like, oh no, okay, just to visualize, oh no, it's not stable, all right? So when it's not stable, what happens is this particular nucleus will find a way to become more stable. So how does it become more stable? Okay, remember, the number of protons and neutrons are not the correct numbers. So what this nucleus then needs to do is it needs to get rid of the additional numbers here and needs to throw it out. Basically, needs to throw stuff out in order to become more stable. So it's easier to throw out than to take in. Like, you don't have floating protons and you say, okay, come, I take extra. It cannot, right? So what this nucleus needs to do in order to become more stable is get rid of all this extra weight that it has so that it can try to achieve a more stable nucleus. Now, the process of throwing this out from its nucleus, and remember the nucleus is like the core of the atom, so it's quite a difficult process and it needs a lot of energy. So that's why radioactivity, there's a lot of energy, and because it comes from the nucleus, that's why it's known as nuclear energy. So in this case, right, when it's going to throw out the radioactive radiation, it is not a predictable process. If you, let's say, have a whole bunch of all the radioisotopes together, okay, you cannot increase or decrease the rate of which the radiation is being released. So the process of this radioactive radiation being thrown out is unpredictable. So it's a spontaneous process. I'm going to write that out here. Basically, the process is spontaneous. That means, for example, if this particular atom wants to throw out its radiation, it will throw out, okay? But you can't make it faster or slower. And let's say another one decides like, okay, now my turn, I'm going to throw it out. It's going to throw out. You cannot predict the order in which nucleus is going to throw out the radiation. So it's very, very spontaneous. And the directions which the radiation could be thrown out is also random. You cannot force it, okay, all of you, please throw in the same direction. Let's go this way, please, everyone. Okay, there's no path, there's no queue, ticketing number, no such thing. If this radioactive material with the many isotopes, many atoms here, they're going to throw out all their radiations, they're going to throw out spontaneous, random, unpredictable. There is nothing that you can do in order to try to hasten or decrease the process or control the direction. So this is what you have to be aware of. So radioactivity exists due to the instability of the nuclei. And when this happens, the process is spontaneous and random. So now that we know where radioactivity comes from, how do these unstable nuclei throw out their extra weight? So it's not, in this case, random, like, okay, I'll randomly throw out protons and neutrons. No. The type of emissions in this case are fixed. There are 3 emissions that you need to know about. That means that if you have an unstable nucleus, that means a radioisotope, an atom that is radioactive, this radioisotope can only release radiation in one of these 3 forms. They can release it as alpha or beta or gamma. So what we're going to focus on are these 3 types of emissions. We're going to look at their characteristics and properties. Let us start first with alpha. Now, alpha can also be written in short form with the Greek letter alpha. If you're not sure how it looks like, this is how you write it. You write alpha like this. It looks like a fish. Okay, so what is alpha? Let me move my face out of the way. So we have in this diagram here, let's say this is not a chocolate chip cookie. No, basically, let's say this is a nucleus of a radioisotope. So the black color part here represents a nucleus, and inside this nucleus we have the protons, which we have marked in blue, and the neutrons, which we have marked in green. Now, what is an alpha particle? So alpha is identical to a helium nucleus. What do we mean by helium nucleus? Okay, so let's recall what you've learned in chemistry, if you take chemistry. So helium is an element which has 2 protons. A typical helium atom will have 2 protons, 2 neutrons, and 2 electrons. But if you note here, we've written the nature here as helium nucleus. So we don't have electrons in the nucleus, right? So inside a helium nucleus, there are only, I'm going to write this down here, it has only 2 protons and 2 neutrons. So if this nucleus was going to throw out an alpha emission, this is how it would look like. That means this very unstable nucleus now needs to get rid of the extra weight. How does it do that? Let's say it gets rid of the extra weight by throwing out alpha. It will take 2 protons and 2 neutrons, put it as a package like this, and this gets thrown out as a particle with 2 protons and 2 neutrons. This thing here, this is an alpha particle. So what happened here is this unstable nucleus has thrown out 2 protons and 2 neutrons out and away, and this thing here that has been thrown out, that's the alpha particle. So this nucleus has now gotten rid of 2 protons and 2 neutrons. So we can say that this radioisotope is an alpha source because it has released an alpha particle. What has happened here is that this radioisotope has undergone alpha decay. Now, if you recall what the term decay means, to decay means to break down into, like biological decay, it breaks it down into its original elements. In this case, for radioactivity, we find that this isotope has kind of like split into 2, right? It's split into 2, one small particle here, and then left behind another bigger particle. So it's kind of like a decay. So this is the concept of radioactive decay. So alpha decay is when this radioisotope has released an alpha particle. So that's why I've written here, alpha decay. So you also need to know how to write the equation to show alpha decay. Okay, I'm going to write this using the nuclide notation, which you should have learned before. If you haven't learned about nuclide notation, please watch my video on nuclide notation. So the nuclide notation in this case is written in the form of AZX. Okay, so AZX, where A is the number of nucleons or the mass number, and Z is the number of protons or the atomic number. So for alpha, because it's identical to a helium nucleus, and now what we mean by, in this case, the identical to a helium nucleus is when you look at this alpha particle, it looks exactly the same as a helium nucleus, right? It's got 2 protons, 2 neutrons. So is it a helium element? Actually, yes, it is. But the difference between this alpha particle and a normal helium atom, besides the fact that this doesn't have electrons, is the source. Helium atoms, basically helium gas, they're usually naturally occurring helium atoms. That means they already exist in nature naturally as helium. This case, though, it came from the inside of another nucleus. So that's what makes this an alpha compared to being a normal helium atom, where it came from. So its backstory, its origins. So that's why this is an alpha particle. But when you look at the alpha on its own, it looks exactly like a helium nucleus. And that's what we mean when we say that basically alpha is like a helium nucleus. So because it looks like a helium nucleus, we can write alpha in this form. Using the nuclide notation, we can write it as 4,2He. So when you see 4,2He, that's basically the same as an alpha particle. Another way to write, which is also accepted, is to write it as 4,2 alpha, using the alpha symbol instead. Okay, so both are acceptable. So when a radioisotope undergoes alpha decay, I'm going to write the equation a little bit at the bottom here. So I'm going to put that at the bottom here. So the equation, I'm going to write the general equation over here first. So assuming that this radioisotope is AZX, I'm going to write here AZX. So this particular radioisotope is going to release an alpha particle. So we start off with AZX, and then to show what happens after the decay, we have an arrow over here. So what we'll write after the arrow here are the products of the decay process. Now, if you look, the decay process here has produced two products. We have the alpha particle, and we also have this nucleus here, which has lost 2 protons and 2 neutrons. So we're going to write here, I'm going to put it this way. This is how we normally write it. The first part is normally this remaining nucleus, and the second part here will be the alpha particle. So although it's not wrong to write alpha first, I'm going to follow normal convention. So we're going to write 4,2He over here, which is basically the alpha particle. If you wrote 4,2 alpha, it's also not wrong. So what goes here would be the remaining nucleus with all the remaining protons and neutrons. This is known as the daughter isotope. I'm just going to write that here so that you are aware. Oops, daughter isotope. I'm going to make this smaller so that it doesn't take up so much space. So basically that's the daughter isotope. So the daughter isotope is the atom that was left behind after throwing out the radioactive radiation. Okay, so if we want to write out the notation for the daughter isotope in this case, we first have to know how many protons and neutrons are left behind. So you can see from the diagram here, this nucleus has already gotten rid of this many protons and neutrons, right? So in terms of the mass number or the number of nucleons, it's lost 4 nucleons. So that means the new number here is less by 4. That means A has dropped by 4. So I'm going to write here as A minus 4. In terms of the number of protons, it's lost 2. So the number of protons, or the atomic number, is now less by 2. So Z has now dropped by 2. So it's Z minus 2. X, if you recall, represents the element. And if you look, the number of protons here have changed. And think about it. Okay. Has the element changed? If the number of protons have changed, has the element changed? If you remember your chemistry, yes, the element has changed, right? Because the type of element of an atom depends on the number of protons. So the proton number has changed, the element has changed. To represent the change in element, I'm just going to write the symbol here as Y, just to show that it's now a different element. So to give you an actual example of a radioisotope that has undergone alpha decay, an example I'm going to use here is americium-241. Okay, so americium, I'll write the name here, americium-241, means it has 241 nucleons. It has 95 protons. Now, americium is an alpha source, and americium is used in things like smoke detectors to detect smoke. And yes, some smoke detectors are radioactive. So americium-241 will throw out an alpha particle to become a new element known as neptunium. And in terms of the numbers, here's how you determine it. You can see, also based on numbers, the number before and after the arrow have to be balanced. So if Americium starts with 2, 4, 1. It's thrown out 4. Use your math skill. 2, 4, 1 minus 4, you will get 2, 3, 7. So you can see the numbers on top must be balanced. So 2, 3, 7 plus 4, you get 2, 4, 1. The same thing will apply for the bottom number. So if you got 95 protons to begin with, and it's thrown out 2 protons in the alpha particle, that means that Neptunium will only have 93 protons. So you can see here the number also is balanced. You've got 95 to begin with, and then at the end, 93 and 2, which the total comes up to 95. So this is an example of how you can write the alpha decay equation. Let's move on now to beta. So beta, on the other hand, is actually the same as an electron. In fact, we typically write it as a high-speed electron. Let me make this a little bit larger so that you can see. In terms of the nuclide notation, it's written as 0 minus 1 E. Or you can write it as 0 minus 1 beta. Now the symbol for beta looks like I look at it like a butterfly. So the alpha is a fish, beta is a butterfly. So you write it this way. It's like a bee with an extended tail. Now, remember, radioactivity comes from the nucleus of the atom. But think about it now. Where's the electron in the nucleus? Now, remember that radioactivity does not include whatever's outside the nucleus. We're only going to focus what's inside the nucleus. So where's the electron? There's no electron, right? So you're like, oh gosh, where does it come from? Okay, so you may or may not know this, but you have to be aware, of course. Now you may know this or you may not, but if you didn't, now you know. You have to be aware that a neutron is made up of 1 proton and 1 electron. So what's going to happen here in this nucleus is one of the neutrons is going to split to become 1 proton and 1 electron. So it will now become a proton, and the electron is thrown out. So this is the electron, and this electron is the beta particle in this case. So that's where this high-speed electron comes from. So the neutron splits, the proton will remain inside the nucleus, and the electrons, because electrons can't reside in the nucleus, it gets thrown out. That's the beta particle. So just like alpha, when you look at a beta particle, it looks identical to an electron. But what makes it different from other normal electrons is its backstory, its origin. It came from the nucleus of an atom. So that's why this is a beta particle. So normal electrons are not beta. This is beta because it came from the nucleus of a radioisotope. So similar to alpha decay, there's also beta decay. So in this case, this radioisotope is a beta source because it's throwing out a beta particle. How do we write the decay equation? Okay, so we're going to use the AZX notation again. So in terms of the AZX notation, starting off with AZX to represent the radioisotope. Okay, again, we have the daughter isotope and the beta particle. So I'm going to put the beta particle at the second part of the equation. So we have over here the daughter isotope. And if you look, okay, has the number of nucleons changed? No, it hasn't, right? Because although this nucleus has lost a neutron, it's gained a proton. So remember, number of nucleons is the total number of protons and neutrons. It has lost a neutron but gained a proton, so the number of nucleons has remained the same. That means the number for A remains the same. The number of protons, on the other hand, has increased by 1, which means that the number of protons now is Z plus 1. Has the element changed? Yes, because remember, the type of element depends on the number of protons. So if the number of protons has changed, so has the element. So to represent the different element, I'm going to write Y. To give you a real-life example of a beta source, carbon-14 is a beta source. So I'm going to write here 14,6 carbon. So this is carbon. Carbon-14 will throw out a beta particle to form nitrogen. The number of nucleons for nitrogen will be 14. And for the number of protons, it's increased by 1. So now it is 7. Similar to alpha decay, you can see that the number on the top must be balanced on both sides of the arrow. The number at the bottom must also be balanced on both sides of the arrow. In this case, because electron is -1, that's why you have 7 plus -1. That gives you 6. So this is what beta decay looks like. Let's go to gamma. Gamma, the symbol normally confuses a lot of students because they think it's Y, so they write letter Y. Actually, how you write gamma is like this. You write gamma like that. So it's like alpha, but pointing down. Now, gamma is rather different from the other two. Gamma is actually an electromagnetic wave. In fact, it's a high frequency electromagnetic wave. If you've learned the electromagnetic wave spectrum under the topic of waves, you would have come across gamma ray. It's on the end of the spectrum with the highest frequency. So that's gamma. Unlike alpha and beta, gamma does not have any mass, because if you recall what you have learned about electromagnetic waves do not have any mass. They don't have any particles in there. So alpha and beta are both particles. Gamma is not a particle. So gamma is a ray. So that's why we can say alpha particle, beta particle, but you must say gamma ray. There's no such thing as a gamma particle. Likewise, you cannot say alpha ray or beta ray. You have to call them alpha particle, beta particle, gamma ray. So if gamma doesn't have any particles, there's no mass, there's no proton, there's no neutron. So what's going on here? That means if you have a radioisotope that releases gamma rays, it is just releasing gamma radiation in a form of very high frequency electromagnetic waves. There are no particles that are being emitted over here. Now, I know some of you are already questioning, but wait a minute. Didn't you just say that radioactivity is due to this, excess weight it's carrying? So if it's releasing gamma rays, but there's no change in terms of the protons and neutrons, how does it become more stable? Good question. So gamma rays normally are not emitted on their own. Gamma rays are normally accompanying the release of alpha or beta. That means as a radioisotope is releasing alpha, it may also release gamma at the same time. Or if it's releasing beta, it may also release gamma at the same time. So normally, gamma radiation accompanies alpha or beta emission. So to give you an example of a gamma decay equation, I'll write it here as an example. So an example of a gamma source is cobalt-60. Cobalt-60 is a widely used gamma source in many industries. So cobalt-60 is not only a strong gamma source, it also happens to release beta at the same time. So That means for the product, there are actually 3 products. So it will release a beta particle as well as gamma. Now, how we write gamma in this case is we just write the gamma symbol. It forms nickel. And because it releases beta, okay, the number of nucleons remain the same and the number of protons increases by 1. So this is an example of how we can write a gamma decay equation. Okay, so remember, gamma always accompanies either alpha or beta. Now, having said that though, that doesn't mean everything that releases alpha will have gamma at the same time, or everything that releases beta has gamma at the same time. No. It can be alpha only, like americium. It can be beta only, like carbon-14. Or it could be alpha and gamma, or beta and gamma. So these are the 3 types of radioactive emissions that you need to know. Now that you know the 3 radioactive emissions of alpha, beta, and gamma, let's look at the characteristics and properties. Before we move on, I just want to address one question that some of you may have. What about X-rays? How come X-rays are not listed here? So if you're curious about X-rays are actually almost the same as gamma. If you recall what you've learned about the electromagnetic wave spectrum, X-rays and gamma rays are on the furthest end of the spectrum where the high frequencies are. So X-ray has a slightly lower frequency than gamma. In terms of the characteristics and properties, X-rays are identical to gamma rays. But why we don't learn about X-rays in radioactive emissions is because X-rays are not necessarily naturally occurring. There are ways to produce X-rays through man-made methods. For example, if you shoot high-speed electrons towards a metal target. As electrons hit the metal target, some of that kinetic energy could be converted into X-rays. So in this topic, we are focusing on the emissions of radioactivity from radioisotopes. Because X-rays are typically not emitted from these radioisotopes, we don't consider X-rays as one of the nuclear emissions in this case. So that's why we only focus on alpha, beta, and gamma. So one of the things that you need to know about are the ionizing effects. What does ionizing effects mean in this case? It means the ability to form ions in other particles. Now, how does it do that? Let's say this is the nucleus of an unstable isotope. We know that this unstable nucleus is going to be releasing radioactive radiation. So I'm not going to draw the protons and neutrons in this case. Just imagine, okay, this is the nucleus that is going to be releasing the radioactive emission. Now, how this unstable nucleus ionizes other particles is like this. Say we've got air particles here. Now, as the radioactive radiation is being released, it's going to cause these air particles to become ions. How does it do that? It's going to physically knock out an electron or more from the shells. Now, let's recall, for the atom, we know there are electrons in the shells. So if the atom loses an electron, basically, it has now an unbalanced charge, and this becomes a positively charged ion. So that's how an ion could be formed. So when an electron is knocked out physically, this now becomes a positively charged ion. So now you have a pair of ions, one positively charged nucleus and an electron. So ionizing effect in this case refers to the ability of the radioisotopes to create a lot of ions. The greater the ionizing effect, the more ions that it can form. So what we're going to look at now is to compare the ionizing effects of alpha, beta, and gamma. Now, one of the ways in which you can consider this is the collision between the alpha particles, beta particles, or gamma with the electrons in the respective atoms. We know alpha is identical to a helium nucleus. Now imagine the mass. It's massive, right? Compare that to an electron. Now I'm just going to redraw this for clarity. Let's say this is the alpha particle. And then we have one tiny dot here, which I'm going to draw. Let's say this now represents the beta. Let's compare first the alpha and beta. So if we have an alpha particle that's moving and collides, and think about how, let's say, a beta particle could move and collide. Which would you think would be easier in terms of knocking out the electron from the shell? The large one. The large one, right? So alpha would have a much greater ionizing effect because it's able to more easily knock out the electron from the shell of another particle. Beta, maybe it would work, maybe it doesn't work, right? And then let's compare that to gamma. Gamma is just, high frequency electromagnetic waves. So if you think, oh, it's easy for it to knock out, but think about it, if like a wind's blowing, is it easy to knock something out compared to if an elephant comes and charges towards, the football, for example, elephant to the football, wind blow. So in this case for gamma, it's not so easy to knock out, right? It may be able to remove the electron if it focuses its energy and happens to be right in that path, possible, but quite difficult. So that's why alpha has the greatest ionizing effect. Beta is a little less, okay? It's somewhere in between, okay? Alpha and gamma. While gamma has the weakest ionizing effect. Another way that you can also consider the ionizing is whether the particles are able to pull the electron out. So alpha, because it is made up of 2 protons and 2 neutrons, that means its charge is positive, right? 2 protons, 2 neutrons. So it's also easier for it to be able to attract the electron out. So even if it doesn't come in contact with the electron, but as it's passing through, let me draw it over here, because of the positive charge, it's also easier compared to the others to pull the electron out away from the shell. So it could either collide and knock out the electron, or it could pull out the electron from its shell. Either way, you find that alpha, it's much stronger in the sense of creating ions. Like beta, it's negative, right? So if it's negative and trying to pull out, it's a little bit more difficult to try to attract anything. So maybe it could repel, but again, it's not as strong because it's got a charge of -1 compared to the alpha, which is a charge of +2. Gamma, it's neutral. Good luck trying to effectively create a lot of ions. Okay, while it potentially could, it's not as strong compared to alpha and beta. So that's a comparison of the ionizing effect. So alpha has the greatest, followed by beta, and gamma has the weakest. Penetrating abilities. So penetrating abilities here refer to the ability of these radioactive radiations to be able to go through objects. If you know the nature of alpha, beta, and gamma, then it's easier to know and understand how they're able to penetrate objects. So alpha, 2 protons, 2 neutrons, right? So because it's got 2 protons, 2 neutrons, that means it is massive. So let's say alpha here, massive. Now imagine alpha, okay, it's a little bit massive compared to beta, which is just an electron, and gamma, it's just, waves. So if all of them were to approach the same obstacle, think about it. Obviously, because gamma doesn't have any particles, it's able to more easily pass through objects. Between alpha and beta, beta is smaller and travels at high speed, it's able to penetrate a little bit more. Alpha is very, very easily stopped. So between the three, alpha has the weakest penetration ability. Beta is between alpha and gamma, while gamma has the greatest penetrating ability. Logical, right? In addition to knowing their penetrating abilities, you also need to know what can stop alpha, beta, and gamma. So when we say what can stop it, it's like the basic minimum that it needs. Alpha is very easily stopped by a thin piece of paper. In addition to paper, alpha can also be stopped by human skin. When I say human skin here, I don't want you to think, oh, we got a human skin, and not that kind of thing, okay? Basically, it means that if we were exposed to an alpha source, the alpha cannot penetrate our human skin to get into the internal organs. Our skin is able to stop alpha from going through in the first place. So that's how easy it is to stop alpha. Beta can be stopped by a few millimeters thickness of aluminium. Gamma needs to be stopped by a few centimeters of lead. So even stopped by is not correct to say. Gamma can be reduced with a few centimeters thick of lead. It's still able to penetrate a little bit, but most of it will be stopped by lead. Besides lead, gamma can also be stopped by concrete, but you need a few meters thickness of concrete. So don't think that, oh, if I stay in my home made of concrete, it's able to stop the gamma rays. No. If you look at how thick your walls are, it's not even 1 meter thick. It's probably about 20 to 30 centimeters thick. You need a few meters thickness of concrete to be able to reduce the gamma rays. So you have to know these shields. These are known as shields. Shield means what could block the gamma radiation. So paper or human skin is able to stop alpha. Beta, you need a few millimeters thickness of aluminium. And gamma, you need a few centimeters thickness of lead or a few meters thickness of concrete. So this is the penetrating abilities of alpha, beta, and gamma. Now let's look at how they deflect in electric fields. So in electric field, in this case, let's say now we take two plates, which we place at a distance from one another, and these plates are connected to a high voltage power supply. So if you're thinking, but if they're not connected, if we place them at a distance, how is the circuit complete? So if you use high voltage, when we say high voltage, we're talking about a few thousand volts. A high voltage power supply can force the circuit to be complete by creating a very high tension electrical field over here. So these two plates are connected to, let's say, a high voltage power supply. So let's say the top here is positive and here is negative. So this creates a very high tension electrical field between these two plates. Now, if we shoot alpha, beta, and gamma in between. Now remember, alpha has a charge of positive 2. So if alpha were to travel into this field, you'll find that alpha tends to be attracted towards the negative plate. Now, whether it actually goes to the plate or misses it depends on how strong the electric field is. Okay? In some cases, yes, it's possible even for the alpha to go all the way to the negative plate. So remember, that's because alpha has a positive charge. Beta, on the other hand, is an electron with a charge of -1. So beta, you'll find, will be attracted towards the positive plate. And in fact, it is able to deflect a lot more quicker compared to alpha. And that's not because of the charge. It's because of the mass. Because alpha has a much greater mass, it's harder to change its direction, right? Due to inertia. If you remember what you've learned about inertia, the greater the mass, the greater the inertia, the more difficult it is to change its direction. Beta is an electron, much smaller mass, so lower inertia, easier to change its deflection. So you find that beta tends to deflect more quickly at a greater angle compared to alpha. Gamma, on the other hand, has no charge. So even if you place it in an electrical field, there is no deflection. It continues in a straight line because it is not affected by electric fields. If the radiation can deflect in an electrical field, it can also deflect in a magnetic field. in this case, the magnetic field has to be drawn in 3D because it's a 3D deflection in this case. So I'm going to draw, let's say, the magnetic field here. Okay, magnet of North Pole here and South Pole on the other side. Because alpha and beta carry charges, they can deflect in a magnetic field. So now let's use yellow to represent alpha. So in order to determine the direction of deflection of alpha, you need to use Fleming's left-hand rule. Now, if you can't remember how to use Fleming's left-hand rule, please watch my video on Fleming's left-hand rule. All right, so let's use our left hand. So for Fleming's left-hand rule, remember, this is force, this is magnet, this is current. So in this case, though, there's no current flow, so which means that the charge is going to be represented by the middle finger. In the case of alpha, because alpha is positive, imagine it's moving from positive to negative, it's the same as current. So have the middle finger follow the alpha direction of positive to negative. So we're going to place and rotate our hand to follow this diagram. I'm going to make my face a little bit larger here so that's easier to follow. So north to south, you need to have your finger point to south. So have your left hand follow mine. A bit closer, right? So this finger needs to point from north to south. This finger needs to follow the charge direction from left to right. So north to south and then left to right. You find that your thumb is pointing up. That means that the alpha particle is going to deflect upwards. So when the alpha particle reaches a magnetic field, it's going to deflect upwards. Okay, it's trying to draw this upwards. So remember, it doesn't just go up, it needs time to change direction to move up. Beta has the opposite charge. It's negative. So obviously, if it's negative, it's going to go in the opposite direction to alpha. Beta is going to move down. Let's say it's in blue. Okay, let's use a different. Okay, so let's say blue. So beta is here. When it comes in, it's going to deflect downwards and it's going to change direction more quickly because of its smaller mass, just like it did for the deflection in electrical fields. If you're wondering how this fits with the Fleming's left-hand rule, because beta is now a negative charge, imagine as if negative trying to go to positive, it's the opposite. So if you're using your middle finger, it's positive to negative. That means for beta, it's got to be the opposite now. So that means have your middle finger, instead of following the beta direction, it goes against the beta direction. So if you're pointing north to south, and then this finger is, you're pointing against the direction of beta, you now have the arrow moving downwards. You have the motion going downwards, which means that beta is deflecting downwards. So that's how Fleming's left-hand rule can be used in this case. Gamma, as discussed earlier, has no charge, so it is not affected by the magnetic field. That means gamma, no deflection at all as it passes through the magnetic field. And this is the deflection of the radiation in magnetic field. And now, let's look at a summary of the properties of the nuclear emissions of alpha, beta, and gamma. So right now, I don't have the slides on full screen because I want to type out the answer as we discuss it so that you can see how to work out the properties of each of the alpha, beta, and gamma, and that way you don't have to memorize so much. So when we talk about the nature of the emission, it means what are they similar to? So alpha is essentially a helium nucleus. Beta is a high-speed electron, but when you're asked to write the nature, you don't have to write high speed. You can just say electron. That will also be acceptable. Gamma is a high-frequency electromagnetic wave. It's okay to just write electromagnetic wave because essentially we just want to know what are alpha, beta, and gamma similar to. For the notation, we write it in the nuclide notation style. And as we had written earlier, alpha is written as 42He, or you can write 42 alpha. Beta is an electron. So you'd write it as 0, -1 e or 0, -1 beta. Gamma doesn't have any nuclide notation because it doesn't have any nucleons. So there's no protons, no neutrons. So in this case, you can just write it using the gamma symbol. Now, when it comes to mass, we don't need to know the actual value of the mass. In this case, we just need to have a comparison between alpha, beta, and gamma. So which one has a great number and which one has a low number. So among the three, alpha, of course, is the heaviest because it's got 4 nucleons, right? So we're going to write here, it's got a great mass. Beta, very low mass. Now, gamma does not have the lowest mass. Gamma does not have any mass. So actually, its mass is 0. Relative charge. So the relative charge in this case means, again, if we're comparing alpha, beta, and gamma, what are the values of the relative charge compared to one another? So is it positive? Is it negative? If so, by how much? So because alpha has 2 protons and 2 neutrons, the 2 protons make it positive 2. The neutrons, of course, are neutral. Beta is an electron, so the charge is -1, while gamma is neutral because it does not carry any charge. Now, for speed, let's work with gamma first because we know that gamma is an electromagnetic wave. And all electromagnetic waves travel with the same speed in vacuum, which is the same as the speed of light. And the reason for that is because light is an electromagnetic wave. So all electromagnetic waves travel with the same speed in vacuum. Hence, if we talk about it in vacuum, gamma rays travel at the speed of light. I'm just going to write here, speed of light. Now, beta is lighter, so it can travel quite fast, although obviously not as fast as the speed of light. Beta particles can actually travel up to 99% of the speed of light. Of course, it can be lower, but it can travel as fast as up to 99% of the speed of light. Alpha is heavier, so of course it's going to travel slower, but still quite fast, faster than you and me, okay? So alpha can travel up to 10% of the speed of light. Range in air. So when we talk about range in air in this case, this is referring to how far the alpha, beta, and gamma can travel if they are not blocked. So because alpha is very heavy, it doesn't travel very far. So it can only travel a few centimeters in air. So it can only travel a few centimeters in air before it tires out. Oh, okay, can't travel anymore. Beta, as an electron, can travel much further. It can travel up to a few meters in air. Gamma can travel even further, of course, because it's an electromagnetic wave. So it can actually travel up to a few hundred meters unimpeded. Ionizing effects is something that we have already covered in the earlier part of the video. So remember that we are comparing the ionizing power between these three. Alpha has the greatest ionizing effect, while beta is in between alpha and gamma. So I'm just going to write here medium, while gamma has the weakest ionizing effect. Whereas for the penetrative ability, gamma has the greatest or the strongest penetrative ability. Beta is in between alpha and gamma, while alpha, of course, has the weakest penetrative ability. And remember, the reason for this is because of the nature of alpha, beta, and gamma. You also need to remember what can stop alpha, beta, and gamma, essentially what the shields are. Alpha can be stopped by paper or human skin. Beta can be stopped by aluminium, while gamma can't really be stopped, but it can be reduced with lead or very thick concrete. And next, we also have to recall the deflection of alpha, beta, and gamma in electrical and magnetic fields. Now, remember that because alpha is positively charged, it will deflect towards the negative plate, while beta, because it's negatively charged, will deflect towards the positive plate. Beta will deflect at a greater angle compared to alpha because of its lower mass. Gamma doesn't carry any charge, hence there's no deflection. In terms of the magnetic field, we would need to determine the direction of deflection using Fleming's left-hand rule. Generally, you need to remember that alpha and beta would deflect in opposite directions, with beta deflecting at a greater angle, again because of its lower mass, while gamma, because it's carrying no charge, has no deflection. So now, just to finish, I'm going to put this on full screen while moving my face out of the way. So these are the properties of alpha, beta, and gamma. And these are the deflections of alpha, beta, and gamma in electric and magnetic fields. And that's it. So if you found this video educational and helpful, please click like and subscribe for more lessons, solutions, and exam strategies from your physics teacher, Ms. Ho. Happy studying!